There is a liquid on this earth that climbs out of its container. You pour it into a cup. You set the cup down. You watch carefully, and the liquid, very slowly, very deliberately, walks up the inside wall, crosses the rim, comes down the outside, and forms a drop at the bottom. The drop falls. Another one forms. Another one falls. The liquid is escaping by itself. Nobody is shaking the cup. Nobody is heating it. Nobody is reaching in and pulling. The thing is climbing out under its own power. Before you tell me this is impossible, let me tell you something else about it. The liquid in question is colder than anything you have ever touched. Colder than dry ice. Colder than liquid nitrogen. Colder, actually, than outer space. It is so cold that the cosmic background radiation, the leftover heat of the universe itself, would feel like a blowtorch next to it. We are talking about a substance that exists only a few thousandths of a degree above absolute zero. The substance is helium-3, the lightest, rarest isotope of the second lightest element on the periodic table. And what it does when you cool it down far enough makes no sense. Not by the rules of any liquid you have ever met. So today, you and I are going to be detectives. We have a crime scene. The crime is the violation of common sense by a liquid. The suspect is helium-3. We will follow the clues, one by one, and we will not let anything off the hook until it confesses what is really going on. Bring your skepticism. Bring your patience. We are going to need both. Let's start with what we know about ordinary liquids. A liquid is supposed to sit there. That's what liquids do. You pour water into a glass, the water sits in the glass. It does not climb up the walls and run off down the outside. Why doesn't it? Well, gravity is pulling it down. The water sticks to the glass a little bit by something we call surface tension and adhesion, and you can see this if you look closely at the meniscus, the little curved lip where the water meets the glass. The water actually does try to climb the wall a tiny amount. Look carefully, and you will see it. The edge curls upward, just a hair. But it stops there. It does not keep climbing. Why? Because the water has weight. It has internal friction, what we call viscosity. And the energy required to lift a column of water up the wall is more than gravity will let you have for free. The water climbs the tiniest fraction of a millimeter, hits a balance, and sits. That is what every liquid in your kitchen does. Olive oil, vinegar, coffee, beer, honey more slowly, but still. They all behave themselves. The meniscus exists because the molecules at the edge are slightly attracted to the glass, but the bulk of the liquid stays put. That is the law of liquids in a gravitational field that has friction in it. And it is a very reliable law. You have never seen anyone's morning tea evacuate the mug by itself. Now I show you helium-3. I cool it down. I pour it into a beaker, and it climbs all the way up the wall, all the way over the top, and all the way back down the outside. The cup empties without any help. What broke? Here is your first clue. Temperature. You cannot do this experiment at room temperature. You cannot do it in a freezer. You cannot do it in a vat of liquid nitrogen, which is already at minus 196 degrees Celsius. That is cold. Much colder than a winter day in Antarctica. Much colder than the dark side of the moon. But it is not cold enough. You cannot even do it in a container of regular liquid helium, helium-4, the kind we use for cooling powerful magnets. Liquid helium-4 boils at about minus 269 degrees Celsius. That is only 4 degrees above absolute zero. To put that in perspective, at 4 degrees above absolute zero, almost everything in the universe has frozen solid. The air, if it were there, would be solid. Hydrogen, the most fluid gas in the universe, would be a slab of ice. Mercury, alcohol, nitrogen, oxygen, every common substance is locked rigid. The only thing still liquid at 4 degrees above absolute zero is helium itself. But 4 degrees is still not cold enough. To see helium-3 climb walls, you have to go 1,000 times colder, about 2/1000ths of a degree above absolute zero, 2 millikelvin. Let me dwell on that for a moment, because the number is hard to grasp. To make helium-3 do this trick, you need a piece of equipment, in my lifetime built only in a few laboratories on the planet, called a dilution refrigerator. It is a beautiful Baroque machine. It works by mixing helium-3 and helium-4 together and pulling them apart in clever stages, using the heat absorbed by the mixing process the way an air conditioner uses evaporating coolant, but pushed to absurd extremes. It is, in essence, a refrigerator inside a refrigerator inside a refrigerator inside a refrigerator. Each stage gets a little bit colder than the last. The final stage, called the mixing chamber, can reach down into the millikelvin range. Below that, special tricks are needed. The temperature it produces is, in a real sense, the coldest temperature in the universe that we know of. The cold of empty space, the cosmic background, sits at about 2.5 degrees above absolute zero, 1,000 times warmer than what's inside that mixing chamber. There is no natural place, anywhere we have looked, that is as cold as the inside of a working dilution refrigerator on Earth. We humans, with our clever steel and clever helium, have made a colder spot than the universe has ever made on its own. So clue number 1, temperature matters. Whatever helium-3 is doing, it only does it when the temperature is unimaginably low, when everything else has thoroughly frozen and gone quiet, when the atoms have almost no thermal motion left at all. That tells us something, but not enough. Cold things are usually boring. Cold things sit still. Cold things become more orderly, more crystalline, more solid. A glass of water put in the freezer becomes ice. Ice does not climb out of the glass. It just sits there. Helium-3, when cooled, does the opposite of getting boring. It becomes more lively, more mobile, more mischievous. That is suspicious. Whatever is in our suspect, the cold is not putting it to sleep. The cold is waking it up. Let's pick up clue number 2. The difference between helium-3 and its close cousin, helium-4. You may not know this, but the helium in a balloon at a birthday party is not all one thing. There are 2 kinds of helium atoms in nature. The common one is helium-4. It has 2 protons, 2 neutrons, and 2 electrons. Almost every helium atom you ever meet is this kind. Maybe 99.999% of them. The other kind, helium-3, has 2 protons, only 1 neutron, and 2 electrons. It is much, much rarer. You can pull tiny amounts of it out of natural gas, or you can produce it through certain nuclear reactions. But you do not bump into it casually walking around. For most purposes, an atom is an atom. If I gave you a flask of helium-3 and a flask of helium-4 and asked you to tell them apart by chemistry, you couldn't. They have the same number of electrons. They form the same bonds, or rather the same lack of bonds, since helium is a noble gas and doesn't bond with much. They are chemically identical twins. But underneath, in the deep machinery of quantum mechanics, they are not the same at all. They are profoundly different. They are, in fact, opposite kinds of beasts. This is going to take a minute, so stay with me, because this is the heart of the mystery. Every fundamental particle in the universe falls into one of 2 camps. We call them fermions and bosons. The names don't matter. What matters is the rule each of them follows. A fermion is an antisocial particle. It cannot occupy the same state as another fermion of its kind. If one fermion is sitting in a particular place, doing a particular thing, no other fermion of the same type is allowed to sit in that exact place doing that exact thing. We call this rule the Pauli exclusion principle. And it is the reason atoms have shells, the reason chemistry exists, the reason matter takes up space at all. Electrons are fermions. Protons are fermions. Neutrons are fermions. The whole structure of ordinary matter is built on this rule of antisocial fermions refusing to share their seats. Picture a stadium where every fermion has assigned seating, and every seat is unique, and no 2 fermions are allowed in the same seat ever, even briefly. That is the world of fermions. Crowded, structured, full of rules. A boson is the opposite. A boson is friendly. A boson loves to be in the same state as another boson. The more bosons you put together, the more they want to pile into the same configuration. Photons, the particles of light, are bosons. That is why you can have a laser where countless photons all march in lockstep, doing the exact same thing at the exact same wavelength. Try to make a laser out of electrons, and you fail, because the electrons would refuse to all be in the same state. Picture instead a dance floor where everyone wants to do the same dance step at the same moment. And they prefer it that way, and the more people doing the step, the better the dance feels. That is the world of bosons. Cooperative, coordinated, eager to share. Now here is the question. Is a helium atom a fermion or a boson? The answer, it turns out, depends on which helium we are talking about. Helium-4 has 2 protons, 2 neutrons, and 2 electrons. 6 fermions total, all bound up tightly into one little package. When you stick 6 fermions together into a single tightly bound bundle, the bundle as a whole behaves like a boson. The fermionness of each piece cancels out in pairs. So a helium-4 atom is, to good approximation, a boson. Friendly, wants to be with its neighbors, wants to share a state. Helium-3 has 2 protons, 1 neutron, and 2 electrons. 5 fermions. Odd number. When you stick 5 fermions together into a tightly bound bundle, the bundle as a whole behaves like a fermion. So a helium-3 atom is a fermion. Antisocial, refuses to share, insists on being a unique snowflake. Same chemistry, opposite quantum statistics. This is clue number 2, and it is enormous, because it means the 2 heliums should behave completely differently when you cool them down to nothing. When you cool helium-4 down to about 2 degrees above absolute zero, something extraordinary happens. The helium-4 atoms, being bosons, do what bosons love to do. They start piling into the same quantum state. A huge fraction of them, billions and billions, all settle into a single shared configuration. The liquid stops being a collection of individual atoms doing individual things. It becomes one giant coherent thing, like one note played on a cosmic instrument. We call this a superfluid. A superfluid has no viscosity. 0. It has no internal friction. It can flow through a tiny hole that an ordinary liquid would never get through. It can swirl in a cup forever, without slowing down. And yes, it climbs walls. This is the famous experiment from the 1930s. Pyotr Kapitsa, in Moscow, and John Allen and Don Misner in Cambridge discovered almost simultaneously that helium-4 below a certain temperature does these impossible things. Bernard Rollin discovered the climbing the walls effect in the same era, and we now call that thin invading layer of superfluid the Rollin film. So you might think, aha, the mystery is solved. Helium-3 climbs walls because it is a superfluid. Same as helium-4. Case closed. Pack up. Go home. That would be a good guess. But it is wrong. This is where it gets interesting. Because helium-3 is a fermion, and fermions are not allowed to do what helium-4 atoms do. A fermion cannot pile into a shared state with all its friends. The Pauli exclusion principle forbids it. If 1,000,000 helium-3 atoms tried to all settle into the same quantum configuration, the universe would say no, you are not allowed. So when we cool helium-3 down to those 2 degrees above absolute zero, where helium-4 has already become a superfluid, helium-3 just sits there. Cold, liquid, boring. It does not climb walls. It does not flow through tiny holes. It is, despite the cold, a perfectly normal liquid. A polite, well-behaved cold liquid that obeys gravity. This was puzzling for a long time. People knew helium-3 was a fermion. They knew it could not become a boson superfluid by the simple bosonic mechanism. They expected then that it would never become a superfluid at all. And for a long time, when they looked, they saw nothing. A normal cold liquid, refusing to do tricks. Yet here we are, decades later, and I am telling you that helium-3 climbs out of the cup. So something else is going on. Some second mechanism. Some quieter mechanism. a trick that needs more cold and more patience. Here is your third clue. The temperature of the helium-4 superfluid transition is around 2 degrees above absolute zero. The temperature of the helium-3 superfluid transition is around 2/1000ths of a degree above absolute zero, a factor of 1,000 colder. Whatever helium-3 is doing, it requires 1,000 times less energy to disrupt than what helium-4 is doing. It is much, much more delicate, much more fragile, much weaker. The slightest amount of thermal jiggling will destroy it. You have to go 1,000 times colder than the helium-4 case to even let the effect take hold. Think about that. We have a fermion, which is not allowed to do the bosonic trick, but somehow, at obscenely low temperatures, it does start doing tricks. It climbs walls. It flows without friction. It conspires. The answer to this puzzle, when we finally got it, was the most beautiful kind of answer in physics. Beautiful because it had already been worked out, in a different context, before anyone realized it would solve helium-3. Let me tell you about the other context first. You know what a superconductor is. You take a metal, like lead or mercury or tin, and you cool it down to a few degrees above absolute zero, and suddenly its electrical resistance disappears, drops to zero. Electrons flow through the metal without losing any energy. You can set up a current in a loop of superconducting wire, walk away, come back a year later, and the current is still flowing exactly as it was. No friction, no loss, a persistent quantum current that just goes and goes. This is strange, because electrons are fermions. They should not be able to do this collective superflow trick, for the same reason helium-3 atoms shouldn't. The Pauli exclusion principle stands in the way. Electrons cannot all settle into the same state. They are antisocial. They have assigned seats, yet they do something equivalent. And the way they do it, worked out by John Bardeen, Leon Cooper, and Robert Schrieffer in the late 1950s, is the most clever piece of cheating in physics. The electrons do not become bosons. They cannot, but they pair up. Two electrons, with opposite spins and opposite momenta, find each other and form a pair. The pair, as a single object, has spin 0. The pair, made of two fermions, behaves like one boson, two antisocial particles joined together, with their fermionness canceling out, dancing as a single bosonic entity. We call these Cooper pairs, and once the electrons form Cooper pairs, the Cooper pairs are allowed to do the bosonic trick. Billions of pairs, all settling into the same shared quantum state, all flowing together coherently, no friction, no resistance. That is superconductivity. The pairing is held together by an indirect attraction. Two electrons in a metal normally repel each other electrically, like charges repel, but in a metal they are sitting in a lattice of positively charged ions, and one electron, as it moves, distorts the lattice slightly, pulling the positive ions toward it. Another electron, far away, feels the pull of those displaced ions. So one electron, by warping its environment, can attract another electron indirectly. The attraction is feeble. It is mediated by lattice vibrations. It only works at very low temperatures, where thermal jiggling won't tear the pair apart. You can picture it like this: two heavy balls rolling on a stretched rubber sheet. Each ball sinks into the sheet a little. The dent created by one ball causes the other ball to roll toward it. They are not attracting each other directly. They are attracting each other through the medium they sit in. The rubber sheet is the lattice. The balls are the electrons. The sheet remembers, briefly, where each ball has been, and that memory pulls the next ball in. Slow, indirect, gentle. That is the Bardeen-Cooper-Schrieffer story. Now, when people started thinking about helium-3, they wondered, could helium-3 atoms do the same trick? Could two helium-3 atoms, both fermions, pair up into a Cooper pair and then condense into a superfluid? The answer turned out to be yes, but it had to be a different kind of pair, because the helium-3 system is different. There is no lattice of positive ions. There are no phonons in the simple sense. The helium-3 atoms themselves have to find some way to attract each other, even though they are similar particles in a quantum liquid sloshing around at the bottom of a flask. The attraction, when it was finally figured out, turned out to be subtle. It involves the way one helium-3 atom polarizes the spin and density of its neighbors. Each helium-3 atom has a tiny magnetic moment because of its odd nucleus, and these moments interact in complicated ways. At very, very low temperatures, the interactions arrange themselves so that two helium-3 atoms find it slightly favorable to walk together in a coordinated way. But the pair is not the simple kind that electrons make in a superconductor. In a superconductor, the two electrons in a Cooper pair have opposite spins. They form what we call a singlet state. The pair has zero total spin, and the pair has zero orbital angular momentum, which means in the simplest sense the two electrons are circling each other in a perfectly spherical, featureless way. As quantum objects go, this is the most boring sort of pair. In helium-3, the pair is more elaborate. The two helium-3 atoms in a pair have parallel spins, not opposite. The pair has a total spin of 1, and the pair has a total orbital angular momentum of 1 as well. It is not just a simple matched-up couple. It is a tiny spinning object with internal structure. We call this a triplet, p-wave Cooper pair. What that means, in plain language, is that the pair is anisotropic. It has a direction. It is not a perfect little spherical thing. It is more like a tiny dumbbell with an axis, and that axis can point various ways. And because of the spins, the pair has a magnetic moment. It can be twisted by magnetic fields. It can be polarized. It carries information about which way it is oriented. This makes superfluid helium-3 strange, in a way that superfluid helium-4 is not. Superfluid helium-4 is a quiet, structureless quantum fluid. Superfluid helium-3 is a quantum fluid with internal degrees of freedom. It has, in some sense, texture. The fluid can twist. It cannot. It can have different superfluid phases, depending on how all those tiny pair axes are arranged in space. In fact, when the experimenters Douglas Osheroff, David Lee, and Robert Richardson at Cornell, in the early 1970s, finally cooled helium-3 down to the millikelvin range, they did not find one superfluid phase. They found two. We call them the A phase and the B phase. They appear at slightly different temperatures and pressures. The A phase has a pair orientation that picks out a special direction in space, like a fluid with a built-in arrow. The B phase is more isotropic, looking the same in all directions when you average it out, but still carrying internal structure underneath. The transition between the normal liquid, the A phase and the B phase, shows up as little jumps and kinks in the measurements, the kind of thing that almost gets dismissed as noise. In fact, when Osheroff first saw the kinks, he thought there was something wrong with the equipment. He was a graduate student. He spent a long time chasing what he assumed was an instrument problem before realizing he had stumbled onto two new phases of matter. That is how it goes. Sometimes. The biggest discoveries arrive disguised as bugs in the apparatus. Once the picture was understood, it became simple to state. Helium-3 atoms, which cannot superfluid as ordinary fermions, learn to dance in pairs. Each pair is a tiny composite boson with an axis and a spin. The pairs condense, all settling into a coherent shared state. And the resulting fluid is a superfluid, with all the properties superfluids have. No viscosity, persistent currents, the ability to flow through cracks too small to admit a single molecule by ordinary means, and yes, the ability to climb walls. So now we are nearly back to the beaker. Let me explain why a superfluid climbs walls. This is the part where we put the clues together and watch the crime scene make sense. Any liquid, even ordinary water, is slightly attracted to the surface of its container. The molecules of the liquid feel forces from the molecules of the wall. These are van der Waals forces. Very short range, very weak, but they exist. Because of this, if you held a flat piece of glass against the surface of a liquid, you would find a microscopically thin film of liquid covering the glass everywhere, a few molecules thick, climbing up the glass for a tiny distance against gravity. In ordinary liquids, this film is a curiosity. It does not do much. It is too thin to matter. The bulk of the liquid is held in place by gravity, and the wisp of film on the wall is just decoration. If liquid wanted to leave the cup by traveling along that film, it would lose most of its energy to friction with the wall, and stall and stop, and never get anywhere. In a superfluid, that thin film becomes a highway. Because superfluid helium has no viscosity, the liquid in that wall film does not get stuck. It does not lose energy to friction. It can flow as freely as a frictionless puck on ice. And once it can flow freely, it does flow. It flows from regions of higher gravitational level to regions of lower gravitational level. It flows out of the cup over the rim. It flows along every surface it can find, redistributing itself, looking for the lowest place it can reach. In an ordinary liquid, the film is too sluggish to matter. In a superfluid, the film is a perfect conduit. So you fill a cup with superfluid helium, set it down, and the entire surface of the cup, inside and out, gets coated with a thin film, all connected. Liquid in the cup is at a higher gravitational level than air outside the cup. The film simply transports the liquid from one to the other, frictionlessly over the rim, until the cup is empty. For helium-3, the same thing happens. Once it has paired up and become a superfluid below those 0.002 of a degree above absolute zero, the Raman film is there. The liquid climbs the wall and runs down the outside, drop by drop by drop, until there is nothing left in the cup. But here is what makes helium-3's wall climbing more strange than helium-4's. In helium-4, the climbing fluid is a simple condensate. There is one phase, no internal structure, nothing weird at the edges. In helium-3, the climbing fluid is a fabric of paired-up fermions, with each pair carrying an axis and a spin. As the fluid flows along the wall, the pair axes can rotate, twist, get pinned by the surface. The film can carry, in principle, all sorts of textures and topological features. People have spent decades studying the kinds of patterns that can form in this fluid. There are predictions, some confirmed, of objects in helium-3 that look like cosmic strings, like tiny analogs of defects in the early universe. The same mathematics, on a tabletop, that we suspect ran through the cosmos in its first moments. When you watch helium-3 climb a wall, you are watching billions of helium atoms, paired up by quantum mechanical conspiracy at temperatures unimaginably cold, walking out of the cup in lockstep, sharing a single coherent quantum state, defying gravity not by magic, but by the simple fact that they have shed all internal friction and decided collectively that they would rather be everywhere on the surface than crowded in the cup. It is, when you really see it, a humbling thing, because everything about it is unfamiliar. The temperature is unearthly. The mechanism is invisible. The behavior of the liquid at the macroscopic level is dictated by a delicate Fermion pair dance going on at the scale of single atoms. There is one more piece of the puzzle worth mentioning, because it is one of the loveliest things about this story. You will sometimes hear people say that quantum mechanics only matters at very small scales, that atoms are quantum mechanical, but tables and chairs are not, that the reason your morning coffee does not climb out of the mug is that you are too big and too warm for quantum mechanics to apply. Helium-3 is a refutation of that claim. The thing that climbs out of the cup is, by laboratory standards, a macroscopic object. You can see the wall film, given the right tools. You can hold it, more or less, if you have a cold enough container. The film is small, but not microscopic. Yet the explanation for why it climbs is purely quantum. There is no classical story you can tell that does justice to it. Cooper pairing, exclusion statistics, condensation into a coherent state. None of that has any analog in the world of pots and pans. What helium-3 shows us is that when you cool matter down enough, when you remove enough thermal noise, the quantum nature of the world stops hiding. It comes up to the surface. It puts on a show, and the show is, in effect, a liquid that does not obey what you thought were the rules of liquids. There is a deeper lesson, too. The Pauli exclusion principle, which forbids fermions from sharing states, looks at first like a barrier to collective behavior. You might think, watching electrons or helium-3 atoms, that they are doomed to be loners, that nothing wonderful can happen with them. But they find a workaround. They pair up. The pairs become bosonic. The bosonic pairs condense. And suddenly the most antisocial particles in physics are dancing together as a single coherent quantum waltz. Nature is more clever than your first guess. The rules are not a cage. The rules are a puzzle. And given enough time and a low enough temperature, particles will find a way to do something beautiful within those rules. So let us look back at our clues, all together, and admire what they tell us. We started with a liquid that climbs out of a cup. We learned that it requires impossible cold, a temperature lower than anywhere in the natural universe, made only inside the carefully tuned guts of dilution refrigerators in a few labs on Earth. We learned that helium-3, despite being chemically a twin of common helium-4, is a fermion, not a boson, and so should not be able to superfluid by the bosonic mechanism. We learned that the way around this is for the helium-3 atoms to pair up, and that the pairs are exotic with parallel spins and orbital angular momentum, like little spinning dumbbells with internal direction. We learned that there are not one but two superfluid phases of helium-3, A and B, with different internal arrangements of the pair axes, found by a graduate student who at first thought he was looking at a malfunction. And we learned that the climbing is the action of a frictionless wall film, the same Rollin mechanism known in helium-4, but here applied to a fluid built of paired fermions in a millikelvin world. The crime is solved. The case is closed. The suspect, helium-3, has confessed. And what it confessed to is more interesting than we expected when we walked into the laboratory. If you ever have the chance to see a working dilution refrigerator with its layers of cooling stages, its mixing chamber a few centimeters across, its electronics shielded from every stray vibration, take the chance. Inside that cold heart, helium-3 is doing its quiet, peculiar dance. Atoms are pairing. Pairs are condensing. A coherent quantum state the size of a thimble is humming along at temperatures lower than anywhere else in the known universe. And if you tilted the apparatus even slightly, that fluid would begin to climb the wall, in absolute silence, with absolute confidence, on its way out of the cup. So I leave you with a thought. A drop of helium-3, at 0.002 of a degree above absolute zero, can carry inside it patterns that look mathematically like the structure of the universe at its earliest moments. Its quantum statistics flip from antisocial to friendly just by pairing up. Its bulk behavior, climbing and flowing where ordinary liquids dare not go, is dictated entirely by quiet rules at the smallest scale. What other tricks do you suppose nature has that we have not yet been clever enough or cold enough to see? Tell me what you think.